The further you go, the worse it gets. Not metaphorically, physically, measurably, in ways that scale with distance in a manner that should genuinely disturb anyone who thinks carefully about what space actually is, rather than what science fiction has taught us to imagine it is. We have a tendency to think of space as a single environment, as though the emptiness between Earth and the Moon is fundamentally the same emptiness as the space between galaxies, just more of it. This is wrong in almost every meaningful way. Space is not a uniform medium that gets more of itself as you travel outward. It is a layered series of increasingly extreme environments, each one operating by rules that the previous one did not prepare you for, each one introducing failure modes that did not exist closer in, each one reducing the probability of survival for any biological system, including the one reading this, in ways that compound rather than simply add. Start with what you know, or think you know. Low Earth orbit, the region where the International Space Station lives, where most human spaceflight has occurred, where the bulk of our experience with humans in space has been accumulated, sits at an altitude of roughly 400 kilometers above Earth's surface. This sounds high. It is not particularly high in any cosmic sense. The atmosphere does not end cleanly at 400 kilometers. It fades gradually, thinning by orders of magnitude with altitude, but never reaching zero until you are genuinely far from Earth. At 400 kilometers, the atmospheric density is approximately 10 to the minus 11 kilograms per cubic meter. Essentially nothing, but not literally nothing. Satellites in low Earth orbit experience measurable atmospheric drag. They require periodic reboosting to maintain altitude. Without correction, they would spiral down and re-enter within months to years, depending on their altitude. At 400 kilometers, you are above the bulk of the atmosphere, but you are inside Earth's magnetic field, the magnetosphere, which extends tens of thousands of kilometers into space and which provides significant protection against the most energetic charged particles streaming from the Sun and from galactic sources. This protection is not complete, but it is real. The radiation environment in low Earth orbit is substantially more benign than it would be without the magnetosphere. Astronauts on the ISS receive roughly 1 millisievert of radiation per day, about 10 times the background radiation on Earth's surface, which is enough to be a health consideration over long missions, but not immediately lethal, not even close. The human body can tolerate this. People have spent over a year continuously in low Earth orbit and returned alive and recoverable. This is where almost all human experience in space has happened, 400 kilometers up, inside the magnetic shield, with communication delays measured in fractions of a second, with emergency return to Earth possible in hours, with resupply missions feasible every few months, with the entire accumulated infrastructure of human civilization available essentially immediately in any meaningful operational sense. This is also where almost everything that makes space dangerous for humans is at its most manageable. Move outward, not far, just to the Moon, 238,000 miles away, 3 days of travel at Apollo-era speeds, a distance that seems enormous by any human experiential standard, but that is, in cosmic terms, essentially zero. The Moon is inside the magnetosphere at some points of its orbit and outside it at others. The magnetosphere is not a perfect sphere, and the Moon's orbit takes it through different regions depending on its position relative to the Sun-Earth line. What this means in practice is that lunar surface operations are exposed to solar particle events, bursts of energetic charged particles from solar flares and coronal mass ejections, with less consistent protection than low Earth orbit provides. A major solar particle event at the lunar surface without adequate shielding can deliver a radiation dose that causes acute radiation syndrome within hours. The Apollo astronauts were lucky. No major solar particle event occurred during any of the lunar surface operations. The Sun cooperated. If it had not, if a coronal mass ejection of the magnitude seen in August of 1972 had occurred while astronauts were on the lunar surface, which it did not but could have, the consequences would have been severe. The August 1972 event, which occurred between Apollo 16 and Apollo 17, delivered doses that would have been dangerous or fatal to astronauts in a thinly shielded spacecraft. Luck is not a long-term strategy for human spaceflight. The Moon also introduces the first meaningful communication delay, roughly 1.3 seconds one way, 2.6 seconds round trip. This is perceptible in real-time conversation, but manageable. Ground controllers on Earth can still provide meaningful support. An astronaut in trouble on the lunar surface can still communicate with Earth in something close to real time. But even at the Moon, the most familiar, most explored, most accessible destination beyond Earth, the environment is dramatically more hostile than low Earth orbit in ways that compound the challenge. No atmosphere, meaning no protection from micrometeorites, which bombard the surface continuously. No magnetic field of its own, meaning direct exposure to solar wind and galactic cosmic rays when the Moon is outside Earth's magnetosphere. Temperature swings from approximately 120 degrees Celsius at lunar noon to minus 170 degrees Celsius in the lunar night. Regolith, lunar dust that is sharp, abrasive, electrostatically charged and damaging to seals, optics and lung tissue in ways that Earth-based testing did not fully anticipate until astronauts actually landed there. The Moon is approximately 3 days away, and it is already substantially more dangerous than low Earth orbit in every measurable dimension. Now go to Mars. Mars sits at an average distance of roughly 225 million kilometers from Earth, though this varies enormously depending on where both planets are in their orbits around the Sun. At closest approach, opposition, the distance shrinks to about 54 million kilometers, and at their most distant, they are separated by over 400 million kilometers. The travel time with current propulsion technology is approximately 7 to 9 months, depending on the trajectory chosen and the orbital mechanics of the particular launch window. 7 to 9 months, each way, in a spacecraft. In those 7 to 9 months, everything that makes space dangerous has more time to act on the humans inside the spacecraft. Radiation accumulates. Not at the relatively manageable rate of the International Space Station, but at the substantially higher rate experienced beyond Earth's magnetosphere, in interplanetary space, where the full flux of galactic cosmic rays and solar particle events reaches the spacecraft with only whatever shielding the vehicle itself provides. Galactic cosmic rays deserve a particular discussion because they represent one of the most fundamentally challenging aspects of deep space radiation, and because they are qualitatively different from the radiation hazards more commonly discussed in the context of solar events. Galactic cosmic rays are high-energy charged particles, primarily protons and heavier atomic nuclei, that originate outside the solar system, accelerated by supernova shock waves and other violent astrophysical processes in the galaxy. They arrive at the inner solar system from all directions, continuously, with energies spanning an enormous range. The most energetic galactic cosmic rays carry energies that dwarf anything achievable in particle accelerators, the so-called ultra-high energy cosmic rays, detected at the Pierre Auger Observatory, have energies exceeding 10 to the 20th electron volts, energies so extreme that a single particle carries the kinetic energy of a baseball thrown at nearly 100 kilometers per hour. The problem with galactic cosmic rays is not their extraordinary maximum energies. Those events are vanishingly rare. The problem is the relentless moderate energy flux that penetrates almost any practical shielding. Unlike solar radiation, which is primarily protons with energies in the million electron volt range, and which can be substantially reduced by several centimeters of water or polyethylene, galactic cosmic rays include heavy nuclei, iron nuclei and other high Z particles, with energies in the billion to 100 billion electron volt range. When these particles pass through shielding material, they do not simply stop. They interact with the material and produce secondary radiation, showers of lighter particles generated by nuclear interactions, that can actually increase the dose received on the other side of the shielding, if the shielding is not thick enough to also stop the secondaries. This means there is a shielding thickness beyond which adding more material makes things better, but below a certain threshold, adding more shielding can make things worse. For practical spacecraft, constrained by mass limits that translate directly into launch costs, achieving the optimal shielding thickness for galactic cosmic rays is extraordinarily difficult. The mass of material required for adequate shielding is enormous by spacecraft standards. NASA estimates that a crew on a mission to Mars and back would receive a radiation dose of approximately 1 to 1.2 sieverts, roughly equivalent to between 20 and 40 chest CT scans administered continuously over the mission duration. This exceeds the current career dose limits set for NASA astronauts, which are themselves set at levels intended to limit lifetime excess cancer risk to no more than 3%. A Mars mission, by current standards, would push astronauts past their career limits in a single mission. These limits are not arbitrary bureaucratic lines. They are calibrated to specific levels of acceptable excess cancer risk based on epidemiological data from atomic bomb survivors, radiation workers, and radiation accident victims. Exceeding them means accepting a higher probability that the radiation received during the mission will eventually cause cancer. Not certainly, not immediately, but with elevated probability over the following decades. And this is the transit. Before anyone sets foot on Mars, 7 to 9 months of accumulated galactic cosmic rays and solar particle events in a spacecraft with whatever shielding mass can be practically launched. The surface of Mars then adds additional radiation exposure because Mars has a very thin atmosphere, about 1% of Earth's atmospheric pressure, providing minimal shielding, and no global magnetic field to deflect charged particles. The Curiosity rover's radiation assessment detector measured radiation on the Martian surface equivalent to roughly 0.6 millisieverts per day, lower than interplanetary space because the surface of Mars, at least, provides shielding from the downward half of the sky, but still substantially higher than the ISS and dramatically higher than Earth's surface. A human on Mars for 500 days, a round number often cited for the surface stay in various Mars mission architectures, would accumulate roughly another 300 millisieverts on the surface, in addition to the transit dose. Total mission doses in the range of 1.5 to 2 sieverts are considered likely for complete Mars missions with current or near-term technology. And this is Mars, the most accessible planetary destination in the solar system. 400 million kilometers at most, 7 to 9 months one way. A surface gravity of 38% of Earth's, a thin but real atmosphere, a day-night cycle of 24 hours and 37 minutes, more similar to Earth's than any other planet. The most benign interplanetary destination available to us. It is already at the edge of what the human body can tolerate from radiation alone. But radiation is not the only danger that scales with distance. Consider communication delay, which transforms from an inconvenience to a fundamental operational constraint as you move outward through the solar system. At the Moon, 2.6 seconds round trip. Frustrating in conversation, but manageable. Guidance can be provided, emergencies can be coordinated. At Mars, between 3 and 22 minutes one way, depending on orbital geometry, meaning 6 to 44 minutes for a round-trip communication exchange. An astronaut who falls and breaks a leg on the Martian surface cannot have that conversation with a flight surgeon on Earth in any meaningful, real-time sense. By the time the message describing the injury arrives on Earth, by the time a response is formulated and transmitted, by the time that response arrives at Mars, the astronaut has already been alone with the injury for at least 6 minutes, and possibly 44 minutes. Medical emergencies that on Earth are resolved in seconds with direct communication must be managed autonomously on Mars. This is not a minor operational inconvenience. It is a fundamental transformation in the nature of crisis response. It means that the crew on Mars must be able to diagnose and treat any medical emergency that could plausibly occur, from appendicitis to cardiac arrest to surgical trauma, without real-time guidance from Earth. The crew must carry the medical knowledge, the equipment, and the psychological capacity to perform procedures that on Earth would require a team of specialists. This requirement does not go away with better training. The underlying constraint, light travel time, is fixed by physics. At Jupiter, between 32 and 52 minutes one way. At Saturn, 68 to 84 minutes. At Neptune, more than 4 hours each way. At Voyager 1's current position, over 22 hours each way. A message sent to Voyager 1 today will not receive a reply until tomorrow. For robotic missions, this is an engineering constraint that teams have learned to work around through autonomous programming and careful mission planning. For human missions, it becomes something more fundamentally challenging. It means that the crew is genuinely, irretrievably alone, in a way that no previous human explorers have experienced. The crew of a mission to Jupiter would be approximately 45 minutes away from any communication with Earth in a one-way sense. They would make every decision affecting their survival without any possibility of real-time input from anyone outside their vehicle. No human crew has ever operated under these conditions. The Apollo astronauts were at most 90 seconds away from Earth in communication terms, an eternity compared to what we're accustomed to, but negligible compared to what outer solar system missions would require. The psychological dimensions of this isolation are poorly understood because they have never been tested at this scale. Antarctica winter overcruise represent the longest duration isolation studies available. Small groups of people at the end of the world, isolated for months, with communication delays of at most seconds. They experience documented psychological effects: irritability, depression, cognitive impairment, interpersonal conflict, that increase with mission duration and isolation. These effects are manageable under the conditions of Antarctic isolation, which include consistent day-night cycles, predictable environments, and the knowledge that rescue is possible within days if a genuine emergency occurs. None of these ameliorating factors apply to a crew at Jupiter. The day-night cycle depends entirely on the spacecraft's rotation and lighting systems, having nothing to do with any external solar cycle that the crew can perceive. The environment outside the hull is uniformly and immediately lethal in every direction. Rescue is not possible on any timescale relevant to a survival situation. But Jupiter introduces dangers that go far beyond communication delay and radiation, dangers specific to its environment that have no analogue in human spaceflight experience. The Jovian system is, by a significant margin, the most radiologically hostile environment in the solar system outside of the Sun itself. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's, and it traps charged particles in radiation belts that dwarf Earth's Van Allen belts in both spatial extent and intensity. The inner radiation belts of Jupiter, the regions closest to the planet where particle flux is highest, are lethal to unshielded humans within minutes and damaging to spacecraft electronics within hours. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, absorbed a total radiation dose over its mission that was orders of magnitude beyond what any spacecraft had previously experienced. Its instruments degraded progressively as the mission continued. Some failed entirely. The spacecraft was designed with radiation shielding that would have been considered extraordinary by any other mission standard, and it still experienced significant radiation-induced degradation. The Juno spacecraft, currently in orbit around Jupiter, carries its sensitive electronics inside a titanium radiation vault, a protective enclosure specifically designed to reduce the radiation dose to the instruments. Even with this vault, Juno's instruments absorb radiation at rates that would destroy unshielded electronics within days. Engineers estimate Juno has received a total dose equivalent to over 100 million dental X-rays during its mission. A human crew in the inner Jovian system would receive doses that no practical spacecraft shielding could reduce to survivable levels. The mass of water or polyethylene required to shield a human habitat against the Jovian radiation belts to survivable dose rates would be measured in hundreds of metric tons, entirely impractical with any foreseeable launch technology. This is not a problem of inadequate engineering, it is a problem of fundamental physics. The particles in Jupiter's radiation belts have energies and fluxes that cannot be stopped by any mass that could practically be carried to Jupiter. Operating in the inner Jovian system, within the orbits of the Galilean moons, would require either a technology for active radiation deflection that does not currently exist, or a fundamentally different approach to human presence, such as remote operation from outside the most intense radiation regions. The Galilean moons themselves vary enormously in their radiation environments. Callisto, the outermost of the four, orbits at a distance that keeps it largely outside the most intense radiation belts and is considered potentially accessible to human missions with manageable radiation doses. Europa, scientifically the most compelling target because of its subsurface ocean, orbits within the intense inner radiation belts and would expose surface crews to doses that represent a lethal threat even with substantial shielding. And this is still within our own solar system, still around a single star that is itself a stable, well-understood main sequence object that will not dramatically change its output on any human-relevant timescale. Still in a region of space where the physics is well characterized, where our models of particle environments are based on decades of spacecraft measurements, where we know what we are dealing with, even if we cannot easily mitigate it. Go further, and the environment becomes not just more hostile, but more uncertain. The outer solar system, beyond Neptune into the Kuiper belt and eventually the Oort cloud, represents a transition zone between the solar wind-dominated environment of the inner and middle solar system and the galactic environment of true interstellar space. The heliosphere, the bubble of solar wind that extends outward from the Sun and defines the boundary of solar influence, ends at the heliopause, the boundary where the solar wind pressure is balanced by the pressure of the interstellar medium. Voyager 1 crossed this boundary in 2012 at approximately 121 astronomical units from the Sun. Beyond the heliopause, in true interstellar space, several things change simultaneously. The solar wind, which provides some screening of galactic cosmic rays within the heliosphere, is absent. The full flux of galactic cosmic rays, unmodulated by the solar wind's magnetic field, reaches any object traveling in interstellar space. The galactic cosmic ray flux in the interstellar medium is estimated to be approximately 2 to 3 times higher than at Earth's orbit, and significantly higher than at any point within the heliosphere during solar maximum conditions, when the solar wind is strongest and its screening most effective. The temperature of the interstellar medium is also counterintuitive. The local interstellar cloud, the region of interstellar space through which the Sun is currently moving, has a temperature of approximately 6,000 Kelvin. This sounds hot. It is hotter than the surface of the Sun, but temperature and heat content are different things. At the density of the interstellar medium, approximately 0.3 atoms per cubic centimeter, the actual heat content is negligible. A spacecraft in interstellar space would radiate heat faster than it absorbed it from the surrounding medium, regardless of the medium's notional temperature, because there are simply too few particles to transfer meaningful thermal energy. The darkness of interstellar space is also qualitatively different from what we experience in the inner solar system. At Earth's orbit, the Sun subtends an angle of about half a degree and provides sufficient light for photography and solar power generation. At Neptune's orbit, approximately 30 astronomical units, the Sun has shrunk to a bright star, providing about 900 times less light than at Earth. Solar power generation becomes impractical at these distances. At 100 astronomical units, roughly the heliopause, the Sun is a very bright star, but provides approximately 10,000 times less light than at Earth. At the distances involved in interstellar travel, the Sun becomes indistinguishable from other bright stars, and the light available from all stellar sources combined is negligible for power generation or navigation. This means interstellar spacecraft must carry their own power sources, nuclear reactors or radioisotope thermoelectric generators, capable of operating for the entire mission duration without resupply or maintenance. The Voyager spacecraft have demonstrated this capability for nearly 5 decades, though their power output has declined by roughly 75% from launch values as the plutonium in their RTGs has decayed. A crewed interstellar mission would require power systems capable of supporting life support, propulsion, communication, and all other systems for decades or centuries, with no possibility of resupply. The communication problem, which became a significant operational constraint at Mars and a fundamental isolation factor at Jupiter, becomes something categorically different in interstellar space. At the distance of the nearest star system, Alpha Centauri at 4.2 light-years, a one-way communication takes 4.2 years. A round-trip exchange takes 8.4 years. No real-time communication is possible in any meaningful sense. The crew of an interstellar mission is not isolated from Earth in the way that Antarctic crews or even Jupiter mission crews would be isolated. They are separated from Earth in time as well as space. Their messages and Earth's responses operate on timescales measured in years, meaning that any person they knew at departure who was more than roughly 50 years old at the time of launch will be dead before any meaningful correspondence can occur. The world they departed will have changed in ways they cannot predict and cannot respond to in real time. This temporal isolation is qualitatively different from anything in previous human experience. Sailors on long voyages knew that home was changing in their absence, but expected to return to a recognizable world. Colonists in the Americas knew they were separated from Europe by months of travel, but maintained cultural and commercial contact, however delayed. An interstellar crew would experience years of communication delay, meaning that events of enormous significance, wars, catastrophes, technological revolutions, the deaths of everyone they knew, could occur and be over, resolved and integrated into the world before the crew even learned they had happened. The crew would receive news not as it happens, but as it happened, in a past that is already resolved from Earth's perspective, but that arrives to the crew as fresh information, demanding a response to something that is already history. The propulsion problem at interstellar distances is perhaps the most fundamental constraint of all, because it determines whether any of the other problems can even be approached. Chemical rockets, the technology that has launched everything humanity has ever put in space, achieve exhaust velocities of approximately 4 to 4.5 kilometers per second for the best chemical propellants, liquid hydrogen and liquid oxygen. The Tsiolkovsky rocket equation relates the achievable change in velocity to the exhaust velocity and the mass ratio, the ratio of initial mass to final mass. For chemical rockets, achieving the velocities needed for interstellar travel within any human-relevant timescale requires mass ratios so extreme as to be physically impossible. At Voyager's speed, approximately 17 kilometers per second relative to the Sun, crossing 1 light year takes approximately 17,500 years. The nearest star system is 4.2 light-years away. Arriving there with Voyager-class propulsion would take approximately 73,000 years. This is not a travel time, it is a geological epoch. Nuclear thermal propulsion, using a nuclear reactor to heat propellant rather than chemical combustion, achieves exhaust velocities roughly twice those of chemical rockets. This halves the travel time, but leaves it in the range of tens of thousands of years. Nuclear pulse propulsion, the Orion concept, using nuclear detonations to propel a spacecraft, could potentially achieve velocities of several percent of the speed of light, reducing the travel time to the nearest star to thousands of years. Still not a human-scale travel time. Fusion propulsion. If controlled nuclear fusion can be achieved and scaled for spacecraft propulsion, which remains one of the great unsolved engineering challenges of our time despite decades of effort, could potentially achieve velocities of 10 to 20% of the speed of light. At 10% of light speed, the nearest star is approximately 42 years away. This is within a human lifetime. Barely. A crew launched young might arrive old. It might not arrive at all, given the unknowns of multi-decade spaceflight without resupply. At 20% of light speed, the target of the breakthrough starshot concept for robotic probes, the transit takes about 21 years. Still a significant fraction of a human lifetime, still longer than most space missions have been planned, but potentially achievable in a single human career. These velocities require energies that dwarf anything in current human energy production. Accelerating a reasonably sized crewed spacecraft to 10% of light speed requires energy equivalent to years of current global energy production. Accelerating to 20% requires even more. The numbers are not physically forbidden, but they are currently fantastical from an engineering and resource perspective. And even at 20% of light speed, which Breakthrough Starshot proposes to achieve for gram-scale robotic probes using an enormous laser array, arriving at the destination and doing anything useful upon arrival requires solving problems that have not been approached. A gram-scale probe arriving at the Alpha Centauri system at 20% of light speed has no mechanism for deceleration. It will pass through the system in hours, conducting whatever observations its tiny instrument package permits during the flyby, and then continue into interstellar space on the far side, never to return, never to be retrieved, transmitting its data back at the speed of light for the following 4 years. This is the best current concept for reaching the nearest star. A gram of electronics in a flyby, transmitting data for 4 years after passing through the destination system for a few hours. Everything about interstellar travel at human scale, crewed spacecraft, deceleration at the destination, any kind of meaningful presence rather than a fleeting flyby, requires either technologies that do not exist or energy budgets that are beyond any foreseeable human civilizational capacity. Not because physics forbids them, because the gap between current capability and required capability is so large that it cannot be bridged by incremental improvement. It requires qualitative leaps in energy production, propulsion physics, materials science, and life support that cannot be timetabled. Now consider what lies beyond the nearest star. The Milky Way is approximately 100,000 light-years in diameter. The nearest large galaxy, Andromeda, is approximately 2.5 million light-years away. The observable universe extends approximately 46 billion light-years in every direction from Earth. These numbers do not scale in any continuous way from what we have discussed. They are not just more of the same. They represent environments in which the physical constraints become so severe that the concept of human travel to those destinations is not a matter of inadequate technology. It is a matter of physical limits that may be fundamental. The expansion of the universe itself becomes relevant at cosmological distances. Galaxies beyond a certain distance are receding from us faster than light, not because they are moving through space at faster than light speed, which special relativity prohibits, but because the space between us and them is expanding at a rate that causes the distance to increase faster than light can cross it. The cosmic event horizon, the boundary beyond which light emitted toward us will never reach us because the intervening space is expanding too fast, sits at approximately 16 billion light-years. Anything beyond this horizon is, in the most literal physical sense, permanently inaccessible to us, regardless of any technology. And within the observable universe, the distances involved are so immense that even the time dilation of relativistic travel, which allows subjective travel time to be compressed by the Lorentz factor at high velocities, cannot make them accessible on human timescales without approaching arbitrarily close to the speed of light, which requires arbitrarily large energies. A spacecraft traveling at 99.9% of the speed of light has a Lorentz factor of approximately 22, meaning 1 year of subjective time on board corresponds to 22 years of Earth time. At 99.999% of light speed, The Lorentz factor approaches approximately 700. A crew travelling at this speed would experience 1 year of subjective time, while 700 years passed on Earth. This means that, in principle, purely in terms of subjective time experienced by the crew, a crew travelling at sufficiently high relativistic velocity could cross the observable universe in a subjective lifetime. The physics permits it. The energy required to achieve these velocities for any practical spacecraft mass exceeds the total energy output of the Sun over its entire main sequence lifetime. And upon arriving, wherever that might be, after subjective decades of travel, the Earth they left would be millions or billions of years in its own future. Everyone they knew would be not just dead, but evolutionary epochs removed from them. Human civilization as they knew it would be as remote from whatever exists on Earth at their destination arrival as the first single-celled organisms are from us. This is the trajectory of the terrifying. It does not plateau. It does not reach a point where the dangers stabilize and the challenges become manageable. It escalates continuously. Each order of magnitude in distance introduces qualitative changes in the environment, the constraints, and the fundamental nature of what travel and presence mean. Low Earth orbit. Challenging but survivable with current technology, demonstrated by decades of human experience. The Moon. More hostile with manageable but real radiation risks, demonstrated by 12 humans who walked on its surface. Mars. At the edge of survivable radiation exposure with current shielding technology, requiring complete medical autonomy with communication delays that transform the nature of crisis response. The outer solar system. Lethal radiation environments in some regions, complete operational isolation, power generation challenges that rule out solar energy, communication delays measured in hours. Interstellar space, galactic cosmic ray flux without heliospheric screening, complete temporal isolation from Earth, propulsion challenges that require energy sources orders of magnitude beyond current capability, communication delays measured in years. Intergalactic space, distances so large that the expansion of the universe itself becomes a relevant physical constraint, timescales so immense that relativistic travel produces temporal dislocations that sever any meaningful connection to the civilization of departure. Each step outward is not more of the same. Each step outward is a qualitative transformation in what space is and what it requires to survive within it. And the most striking thing about this progression is that it is not hypothetical. It is not science fiction extrapolation. Every element of it is derived from physics that has been tested, measured, and confirmed to extraordinary precision. The radiation environments are measured by spacecraft instruments. The communication delays are calculated from the speed of light and measured distances. The energy requirements for propulsion are derived from special relativity and the rocket equation. The expansion of the universe is measured by the redshift of distant galaxies and the cosmic microwave background. The universe is not getting more dangerous as you travel further from Earth because it has something against exploration. It is getting more dangerous because it operates by physical laws that do not scale linearly with distance, that introduce qualitatively new phenomena at each scale, and that were not in any way arranged for the convenience of biological systems that evolved to survive in the particular physical conditions of one planet's surface. We exist in a very specific niche, a thin shell of atmosphere on a rocky planet in the inner zone of a stable star that is extraordinarily hospitable to us because we evolved within it. Everything outside that niche is hostile to varying degrees, and the degree of hostility is not constant with distance. It accelerates. There is a specific way to understand this acceleration that cuts through the abstraction and makes it viscerally concrete. Think about what your body requires to stay alive, not what it prefers, what it requires in the minimum necessary sense. Oxygen, at a partial pressure sufficient to maintain blood oxygen saturation above about 90%. Temperature between roughly 0 and approximately 45 degrees Celsius for basic cellular function, a range that narrows considerably when you consider what tissues can actually survive. Water, continuously, because the body loses it constantly through respiration and perspiration and cannot store meaningful reserves. Food, providing calories and micronutrients that the body cannot synthesize from raw materials. Pressure, ambient atmospheric pressure that prevents body fluids from boiling, that keeps the lungs inflated at a functional volume, that maintains the mechanical integrity of tissues that evolved under one atmosphere of pressure. Gravity, or something that replaces its physiological functions, because the human body in zero gravity begins breaking down in ways that are not merely uncomfortable, but structurally damaging over timescales of months. On Earth's surface, all of these requirements are met by the environment as a default condition. Air is everywhere. Temperature in most inhabited regions is survivable with clothing. Water flows. Food grows. One atmosphere of pressure is the baseline. Gravity is constant. In low Earth orbit, every one of these requirements must be actively maintained by life support systems that require continuous power, continuous consumables, and continuous maintenance. The moment the systems fail in any critical way, the time until death is measured in minutes for oxygen or pressure, hours to days for temperature, days for water. The ISS has redundant systems, specifically because any single system failure without backup would eventually be fatal. This is the baseline cost of existing in space at all, the cost of replacing an environment that provides these requirements automatically with systems that provide them artificially. At low Earth orbit, this cost is manageable because resupply is feasible and emergency return is possible. The life support systems on the ISS are not required to operate indefinitely without maintenance or consumables because resupply missions arrive every few months, and the crew can evacuate to Earth in hours if the systems fail catastrophically. Now trace what happens to each of these requirements as you move outward. Oxygen. In low Earth orbit, oxygen is resupplied regularly, and the ISS uses electrolysis of water to generate oxygen from water, creating a partially closed loop. On Mars missions, oxygen could be generated from the Martian carbon dioxide atmosphere through chemical reactions. The MOXIE experiment on the Perseverance rover demonstrated this in principle. In the outer solar system, water ice is available on many moons as a feedstock for electrolysis. In interstellar space, there is no external source. All oxygen must be carried or generated through completely closed-loop life support systems, systems that recycle every molecule with zero net loss over mission durations measured in decades. Zero net loss over decades is not the same engineering challenge as low net loss over months. The difference is approximately an order of magnitude in the required reliability of every component, every seal, every valve, every chemical process in the life support system. Current life support technology achieves recovery rates for water and oxygen on the ISS of approximately 90 to 95%, adequate for months to a year of operation between resupply, but insufficient for multi-decade interstellar missions, where even a 1% loss rate per year compounds to catastrophic depletion over the timescales involved. Temperature. On the ISS, thermal management involves radiating waste heat to space using external radiators, while protecting inhabited areas from extremes. This is well understood engineering. On Mars, the thin atmosphere and relatively close proximity to the Sun keep thermal management within the range of achievable technology. In the outer solar system, the absence of solar heating means spacecraft must generate their own heat from nuclear sources or waste heat from power systems. Passive heating from the Sun is negligible beyond roughly 4 or 5 astronomical units. In interstellar space, the spacecraft is a tiny, warm object in an environment that is essentially 3 degrees above absolute zero, the temperature of the cosmic microwave background. The thermal management challenge is maintaining warmth against a universe-scale heat sink, while also preventing waste heat from building up inside the spacecraft to dangerous levels. Water. On the ISS, water is partly recycled and partly resupplied. A 1-year ISS mission consumes approximately 1,000 to 2,000 kilograms of water per crew member when accounting for all uses: drinking, food rehydration, hygiene, oxygen generation. A 10-year interstellar transit with a crew of 4 would require either 10 to 20 metric tons of water resupply, impossible without a source, or a water recycling system that operates with near perfect efficiency for the entire duration. The current ISS water recovery system achieves recovery rates of approximately 90 to 93%. At 90% recovery, a starting supply of 10 metric tons of water shrinks to approximately 3.5 metric tons after 10 years of the remaining 10% being lost each year. A 7 metric ton shortfall assuming no external source. Closing this gap requires either dramatically better recycling efficiency or an external water source in interstellar space, where no such source exists. Food. Food is the most difficult of the basic requirements to close loop in space. Plants can be grown, but the mass and volume requirements for producing sufficient calories for a human crew through agriculture are substantial. The efficiency of converting spacecraft resources into human calories through plant growth is low compared to carrying pre-packaged food. For short missions, months, carrying food is practical. For years-long missions, growing food becomes necessary because the mass of pre-packaged food for multi-year missions exceeds any practical payload limit. For multi-decade interstellar missions, growing food is not optional but mandatory, and doing so requires maintaining a functioning agricultural ecosystem: lighting, soil or hydroponic substrates, atmospheric composition control for plant growth, pest management, genetic diversity in the seed stock for the entire mission duration, with no resupply and no ability to import replacement components. No such system has ever been built. The closest analogue, the Biosphere 2 experiment in Arizona in the early 1990s, demonstrated how difficult closed-loop ecological support is, even on Earth, with external support available. The Biosphere 2 crew experienced oxygen depletion caused by microbial activity in the soil, insufficient food production requiring caloric restriction, and numerous other system failures that required multiple breaches of the sealed environment to address. The experiment lasted 2 years with 8 people. An interstellar mission would require the same capability for decades, with no possibility of external intervention. Pressure. Maintaining cabin pressure against the vacuum of space is a mature engineering problem. Spacecraft hulls are well understood pressure vessels. But the failure modes become more severe with distance because repair options decrease. A micrometeorite impact that causes a slow leak on the ISS is detectable, locatable, and patchable within hours with materials and crew available on orbit. A similar impact on an interstellar spacecraft would require the same repair capability, but with no possibility of resupply for the patch materials, no ground crew support for troubleshooting, and no option to evacuate while repairs are made. At interstellar distances, every system failure becomes an autonomous repair problem that must be solvable with whatever materials and expertise are present on the spacecraft. There are no spare parts delivered from Earth. There are no engineers on the ground who can examine the actual failed component. There is no option to hold the mission in a stable configuration while support is organized. The crew must fix it, with what they have, in whatever time the failure mode allows, with no external help and no fallback option. This requirement for complete autonomous repair capability across every system on a complex spacecraft over a multi-decade mission has never been achieved or even seriously designed for. The ISS requires continuous resupply of spare parts and periodic replacement of components that wear out or fail. The Voyager spacecraft, which have operated for nearly 50 years, have experienced component failures that were managed through ground commands and software updates. Possible because they are robotic. Human crews cannot be similarly managed from Earth across interstellar communication delays. Now consider what these requirements do when they interact with each other. Oxygen generation through electrolysis requires power. Power comes from nuclear reactors, which require cooling, which requires thermal management systems, which have mechanical components that wear out over decades of continuous operation, and must be maintained or replaced from onboard stores. Water recycling requires power, and chemical processing consumables that are gradually consumed and must be replenished from onboard stores or manufactured from raw materials available within the spacecraft system. Food production requires light, artificial light at distances where solar is impractical, which requires power, which requires the nuclear systems that require cooling, that requires the thermal management, that requires the mechanical components that require maintenance. Every system depends on every other system. The failure of any one of them propagates through the network of dependencies in ways that can cascade catastrophically. Life support systems on Earth are embedded in a planet-scale ecosystem that provides redundancy at a scale no spacecraft can match. If the oxygen recycling system fails on Earth, you walk outside and breathe air. If the food production system fails on Earth, you go to a store. If the thermal management system fails on Earth, you put on a coat. On an interstellar spacecraft, none of these alternatives exist. The spacecraft is the total environment. It either works in all of its interconnected complexity, or it does not work at all. This systemic interdependence, the way that every life-critical system on a spacecraft depends on every other, is itself one of the most underappreciated dangers of deep space travel. It is not one danger to be mitigated, but a property of the environment that emerges from the absence of any external support. The danger is structural. It is built into the situation by the removal of the planetary ecosystem that normally provides redundancy. At Mars distance, this systemic interdependence is already a serious engineering challenge. Communication delays mean that system failures must be resolved autonomously, but the mission duration, roughly 2.5 to 3 years for a round trip with surface stay, is short enough that careful pre-mission design can anticipate most failure modes and stock spare parts accordingly. At Jupiter distance, the mission duration lengthens and the communication delay worsens, reducing the ability to get ground support and increasing the mission duration over which systems must function without resupply. At interstellar distances, the systemic interdependence becomes the defining challenge, more fundamental even than propulsion, because even if you could somehow reach another star, you must survive the journey. Consider the human body itself, which is also a system that degrades with exposure to the space environment in ways that scale with mission duration. The effects of microgravity on the human body are among the best studied aspects of long-duration spaceflight, and they are deeply concerning. In the absence of gravitational loading, the musculoskeletal system, bones and muscles, loses mass and strength at rates that, unchecked, would leave astronauts unable to function on a planetary surface after extended missions. The current countermeasure is exercise, 2 hours per day of resistance and cardiovascular exercise on the ISS, a substantial portion of the crew's waking hours, specifically to slow the rate of bone and muscle loss. Even with this exercise, astronauts returning from 6-month ISS missions require weeks to months of rehabilitation before returning to full function on Earth. Astronauts returning from 12-month missions require longer. The extrapolation to multi-year missions is not straightforward because the body does not adapt indefinitely to microgravity exercise regimes. The rate of bone and muscle loss may plateau at some point, but we do not have data from missions long enough to know where that plateau is or whether rehabilitation from very long missions is practically achievable. The cardiovascular system adapts to microgravity in ways that compromise its function under gravity. Without gravitational loading driving blood toward the lower extremities, the cardiovascular system redistributes blood volume toward the upper body, causing what astronauts experience as facial puffiness and nasal congestion in the early days of a mission. Over longer missions, the heart itself remodels. It works less hard against the reduced preload requirements of microgravity and becomes less efficient at pumping blood against gravity. Upon return to gravity, the cardiovascular system must rapidly readapt, which is a period of significant physiological stress. The immune system is affected by both microgravity and radiation. Immune function appears to be suppressed in spaceflight. The mechanisms are not fully understood, but both stress hormones and direct effects of microgravity on immune cell function appear to contribute. Suppressed immune function, combined with the confined quarters of a spacecraft, where any infectious agent can spread rapidly through the crew, creates risks that antibiotics and antivirals can mitigate but not eliminate. On a multi-year mission to another star, the crew cannot be resupplied with new pharmaceuticals if resistant pathogens emerge or if new illness develops that requires treatments not in the medical kit. The visual system has emerged as one of the most concerning effects of long-duration spaceflight following the ISS era. Significant fractions of long-duration astronauts, particularly those on missions of 6 months or more, have experienced changes to their vision and to the physical structure of the eye and brain. The leading explanation involves increased intracranial pressure in microgravity. Without gravity pulling cerebrospinal fluid downward, pressure in the skull and behind the eyes increases, causing structural changes to the optic disc and sometimes impairing vision that may not fully reverse after return to Earth. The significance of this for long-duration missions is not fully understood because we have limited data from missions beyond approximately 1 year. Scott Kelly's 1-year ISS mission provided data that suggested the effects worsen with mission duration but may plateau. but one data point at 1 year is not sufficient to characterize the long-term trajectory. For a mission to another star taking decades, the cumulative intracranial pressure effect over that duration could be severely disabling. Radiation damages DNA. Not all DNA damage is repaired. Some fraction of radiation-induced damage leads to mutations that persist, and some of these mutations increase the risk of cancer. This is a probabilistic effect rather than a threshold effect. There is no dose below which the cancer risk is zero, only doses at which the excess risk is small relative to baseline. The radiation doses encountered in deep space, particularly from galactic cosmic rays, produce not only the carcinogenic risks from DNA damage, but also direct effects on the central nervous system that are now beginning to be understood. Recent research using mouse models exposed to simulated space radiation has found effects on cognitive function, impaired spatial navigation, reduced performance on learning tasks, behavioral changes consistent with anxiety and depression that appear to result from direct radiation damage to neurons in the brain and from radiation-induced inflammation in the central nervous system. The particles responsible for these effects are primarily the high-energy heavy ions in the galactic cosmic ray spectrum, the same particles that are difficult to shield against. Whether these cognitive effects would occur in humans at the doses received during interplanetary or interstellar travel, and at what severity and reversibility, is not fully known, because we cannot ethically expose humans to the relevant doses in controlled experiments. The animal data suggests the risks are real and potentially significant, meaning that a crew on an interstellar mission might arrive at the destination with measurably impaired cognitive function compared to their baseline at departure, as a consequence of decades of accumulated radiation exposure to their central nervous system. The compounding of these effects, musculoskeletal degradation, cardiovascular remodeling, immune suppression, visual system damage, cognitive impairment from radiation, over mission durations measured in decades, creates a picture of the human body as a system that is not designed for long-duration space travel, and that accumulates damage in multiple organ systems simultaneously when exposed to the space environment. The countermeasures available, exercise, pharmacological interventions, artificial gravity, if achievable, can slow these processes, but cannot fully prevent them. Artificial gravity, rotating the spacecraft to create a centrifugal acceleration that mimics gravity, is the most theoretically attractive countermeasure for the musculoskeletal and cardiovascular effects of microgravity. It is also practically complex. A rotating habitat large enough to provide effective artificial gravity without inducing motion sickness from the Coriolis effects of rotation requires a rotation radius of roughly 10 to 50 meters and rotation rates of roughly 2 to 6 rotations per minute, depending on the design goals. This requires a spacecraft considerably larger and more mechanically complex than anything currently envisioned, and introduces engineering challenges related to the rotating joint at the center of the rotation that must transmit power and communications between the rotating section and non-rotating components without failure over mission durations measured in decades. Nothing in this list of challenges is physically forbidden. The laws of physics do not prevent humans from surviving in space for long periods. They impose constraints, and engineering can work within constraints. But the constraints scale with distance and mission duration in ways that outpace the rate of technological progress, and the compounding of multiple systems degrading simultaneously, physical, physiological, psychological, creates a combined challenge whose difficulty is not the sum of the individual challenges, but something greater. Consider the psychological dimension separately, because it is often underweighted in technical discussions of deep space travel, and because it may be the binding constraint before any of the physical challenges become overwhelming. Human beings are social animals, not in a soft, preferential sense, in a hard, neurological sense. The human brain requires social interaction to function normally. Isolation and loneliness activate the same neural pathways as physical pain. They are processed as threats by the nervous system because, for social primates, isolation was in fact a threat. Isolation leads to measurable deterioration in cognitive function, emotional regulation, sleep quality, immune function, and physical health. These are not consequences of weakness or inadequate preparation. They are consequences of neurological architecture that evolved for a specific social environment. No amount of crew selection or psychological training makes humans non-social. The best available crew members will still have neurological systems that require social connection, variety in their physical environment, meaningful activity with observable consequences, and some form of connection to the larger human community. A spacecraft provides very limited amounts of all of these. The confinement of a spacecraft is extreme by any historical comparison. Antarctic winter-over crews experience months of isolation in a building, but the building contains common areas, private spaces, and an outdoor environment they can access in survival gear. Submarines are confined, but have regular contact with the surface world, and missions measured in months. No environment in human history approximates the combination of physical confinement, complete social isolation from the outside world, mission duration in years to decades, and absence of any ability to leave that characterizes an interstellar spacecraft. The most relevant research comes from analog environments, simulations of long-duration isolation conducted specifically to study psychological effects. The Mars 500 experiment, a 520-day simulated Mars mission conducted in Moscow from 2010 to 2011, provided some data on crew psychology over mission durations approaching the length of a Mars round trip. The crew experienced sleep disturbances, reduced physical activity, mild mood disruption, and interpersonal tensions that required management, though no catastrophic psychological breakdowns occurred. The study showed that a carefully selected and prepared crew can maintain reasonable psychological function over the relevant timescale. But it was conducted in a facility in Moscow, with the knowledge that exit was possible at any time, with communication to the outside world in real time, and with simulated, rather than actual, life or death consequences to any system failure. Real psychological effects of true isolation, with genuine life or death stakes and no possibility of exit over multi-year missions, are unknown because they have never been experienced. The analog data provides lower bounds on the challenges. Actual deep space missions would face greater challenges, but cannot provide upper bounds because the conditions cannot be fully replicated. The group dynamics of a small crew over years to decades in confinement with no external social input represent a social system that has no precedent. Interpersonal conflicts that in normal life contexts are resolved by distance, by the ability of one party to leave and reduce contact with another, must be resolved within the spacecraft because there is nowhere to go. The same small group of people seeing each other every day for years, making collective decisions about resource allocation and mission priorities and medical care and interpersonal behavior, with no external authority or exit option, is a social configuration that history has never quite produced. Some small isolated communities, monasteries, remote research stations, island settlements, provide partial analogues. Their lesson is that some such communities function well for extended periods, and others collapse into conflict or dysfunction. The difference tends to be highly specific to the particular individuals involved, their cultural backgrounds, their conflict resolution approaches, and a degree of luck in interpersonal chemistry that cannot be reliably predicted or engineered. For a small crew on an interstellar mission, bad luck in interpersonal chemistry is not an inconvenience. It is a mission-threatening event. These psychological challenges compound with the physical ones in ways that are not additive. A crew experiencing low morale and interpersonal conflict is less effective at maintaining complex technical systems. A crew member experiencing depression or anxiety has reduced cognitive performance precisely when high cognitive performance is required for system maintenance and emergency response. The psychological state of the crew is not independent of the physical condition of the spacecraft. They interact, with deterioration in either potentially triggering deterioration in the other. Now step back from the individual mission and look at the challenge at civilizational scale. An interstellar mission, any interstellar mission, crewed or robotic, requires a level of civilizational commitment that has no historical precedent. The pyramids of Giza were built over approximately 20 years. The great cathedrals of medieval Europe were sometimes built over centuries. The interstate highway system of the United States was constructed over roughly 35 years. The Manhattan Project, perhaps the most intensively resourced single technological effort in history, was completed in 3 years. The Apollo program, the most comparable in scope to what interstellar missions would require, took approximately 8 years from commitment to first lunar landing, and required at its peak roughly 4% of the United States federal budget. An interstellar mission to the nearest star, at velocities achievable in any near-term timeframe, would require decades of sustained effort at resource levels comparable to or exceeding Apollo, with no definitive result until the mission is complete, which for a crewed mission might be 60 to 80 years after initiation, and for a robotic flyby mission at 20% of light speed would be approximately 24 years from launch to first data return. The institutions funding the mission at initiation would need to be sustained for decades. The people who began the work would retire and die before seeing results. The political will to maintain funding across multiple election cycles, economic crises, and shifts in public priorities would need to hold for longer than any comparable historical program has held. Human institutions have demonstrated the ability to sustain scientific programs over multi-decade timescales. Voyager, now nearly 50 years into its mission, is the most striking example. But Voyager required a level of ongoing resource commitment, primarily in maintaining the Deep Space Network tracking stations, that is modest compared to what interstellar missions would require. Scaling from maintaining a radio tracking network for robotic probes to sustaining a multi-generational crewed mission program represents a qualitative increase in the institutional challenge. The Voyager spacecraft also illustrates something important about the durability of technology. Designed and built in the early 1970s with the technology of that era, they are still functioning nearly 50 years later, albeit with degraded capability and dwindling power. The longevity of well-designed robotic systems is genuinely impressive. But the engineering philosophy that makes them durable, simplicity, redundancy, conservative margins, becomes harder to maintain as mission complexity increases. A crewed spacecraft for an interstellar mission would be orders of magnitude more complex than Voyager, with orders of magnitude more components that could fail, maintained by a crew rather than designed to operate autonomously without maintenance. The Fermi paradox, the observation that we see no evidence of other civilizations, despite the universe being old and large enough that many should have developed interstellar capability, is sometimes cited in discussions of interstellar travel, and it is worth noting what the scaling of space dangers might contribute to this silence. If the challenges described here, radiation, systemic life support interdependence, physiological degradation, psychological limits, propulsion energy requirements, civilizational commitment scale, represent fundamental constraints rather than engineering problems awaiting better solutions, they might constitute part of a great filter that applies to all technological civilizations. Not necessarily because the physics prevents interstellar travel, but because the combination of technical and social challenges required to achieve it might regularly exceed what civilizations can sustain before other pressures intervene. This is speculative, and there are good reasons to doubt that the great filter sits at interstellar travel rather than at some earlier bottleneck. But the observation that the challenges do not diminish with distance, that they accelerate, compounding in ways that become qualitatively more difficult at each order of magnitude in scale, provides at least a physically coherent basis for why interstellar travel might be rare, even for civilizations that have developed the desire to attempt it. The universe, viewed through the lens of what it takes to survive within it at increasing distances from any hospitable starting point, looks less like an open frontier and more like a series of nested barriers, each one harder than the last, each one requiring a qualitative rather than quantitative improvement in capability to overcome. The first barrier, leaving Earth's surface, was overcome 65 years ago. The second, operating in space for extended periods in low Earth orbit, has been ongoing for decades. The third, operating beyond the protection of the magnetosphere for months at a time, has been attempted but never for the durations needed for Mars and beyond. The fourth, operating in the outer solar system's radiation environments, has been achieved robotically, but never with human presence. The fifth, crossing into true interstellar space, has been achieved robotically by a single spacecraft, barely, with no life support and no requirement to return. Each barrier that has been crossed required something qualitatively new, not just more of what solved the previous barrier. Rocket technology crossed the first. Life support systems crossed the second. Radiation shielding and medical protocols are the frontier of the third. Nuclear power and autonomous systems are the frontier of the fourth. Propulsion physics and closed-loop life support at scales not yet achieved are the frontier of the fifth. What makes the fifth barrier qualitatively different from all previous ones is not just the magnitude of the challenge, but the absence of intermediate steps. There is no low-risk way to test the systems required for interstellar travel on shorter missions, because the systems are specifically adapted to mission durations and distances that have no shorter analogue. A life support system that must function for 40 years with no resupply cannot be meaningfully tested on a 5-year mission. The failure modes that emerge after decade timescales cannot be detected on timescales an order of magnitude shorter. This is not an argument that interstellar travel is impossible. It is an argument that the approach to it is categorically different from the approach to previous barriers, that there is no stepwise progression of test missions that builds toward it in the way that Mercury led to Gemini, led to Apollo, led to Skylab, led to the Space Shuttle, led to the ISS. The step from where we are to interstellar capability is so large that no intermediate step quite bridges it. Which brings us back to the beginning. The further you go, the worse it gets. This is not a counsel of despair, it is an accurate description of what space is, a set of environments layered outward from the specific niche in which biological life evolved, each layer more hostile than the one before it, each layer requiring qualitatively more capability to survive within it, each layer further from the conditions that 4 billion years of evolution specifically optimized biological systems to handle. We exist at the bottom of this stack, in the thinnest possible margin of survivability, maintained by a planetary system that has been accidentally ideal for our existence for billions of years. When we step off this platform, as we have in low Earth orbit, and as we eventually will further out, we carry our biology with us into environments that biology was not made for. The question of how far we can go is ultimately a question about the gap between what our biology can tolerate and what our technology can provide in compensation. In low Earth orbit, that gap is large, and technology adequately bridges it. At Mars, it narrows. In the outer solar system, it narrows further. In interstellar space, it is at its most extreme. The universe is not trying to keep us home. It is not hostile in any intentional sense. It is simply what it is: vast, cold, radiated, pressureless, dark beyond any darkness Earth has ever shown us, and indifferent to the metabolic requirements of carbon-based organisms that happen to develop on one particular rocky planet orbiting one particular unremarkable star. The further you go into that indifference, the more of it there is. And the human project of going there anyway, of building the systems and developing the understanding to push each barrier outward by some margin, is one of the more remarkable things that the universe has accidentally produced. A small pocket of self-awareness, surrounded by indifference on all sides, choosing to understand the indifference rather than simply inhabiting the pocket. That choice does not make the distances shorter. It does not make the radiation less energetic, or the communication delays smaller, or the life support requirements more achievable. The physics remains what it is, but it changes what the distances mean. Not from the universe's perspective, the universe has no perspective. From ours. There is a specific number that clarifies the entire picture with unusual precision. 1 gravity, 9.8 meters per second squared. The acceleration that Earth's mass exerts on any object at its surface. This number is not arbitrary. It is not a coincidence. It is the specific gravitational acceleration produced by a planet of Earth's mass and radius, and it is the acceleration under which every biological system on this planet evolved over 4 billion years. Your heart is sized to pump blood against 1 gravity. Your bones are structured to support your body weight under 1 gravity. Your vestibular system, the apparatus in your inner ear that tells you which way is up, is calibrated to 1 gravity. Your immune system's function, your sleep architecture, the fluid dynamics of cerebrospinal fluid in your skull, the mechanical loading that stimulates bone turnover, all of it calibrated to 1 gravity. Remove that gravity, and all of these systems begin to drift from their calibrated states simultaneously. Not catastrophically at first. The human body is adaptable over short time scales, but persistently, in ways that compound over months and years, in ways that countermeasures can slow but not stop, in ways that become more severe the longer the exposure continues. This calibration to 1 gravity is not something that training can overcome. It is built into the biochemistry. Bone mass is maintained by mechanical loading. The stress of body weight transmitted through the skeleton signals the cells responsible for bone maintenance to keep producing bone tissue. Remove the mechanical loading and the signal diminishes and bone density decreases. This is not a psychological response to the absence of gravity. It is a cellular response to the absence of mechanical stress. No amount of motivation or preparation changes the biochemistry. The same applies to cardiovascular function, to immune function, to the intracranial pressure effects on vision, to the redistribution of body fluids. These are not problems that better astronauts can solve. They are properties of human biology, operating outside its design parameters. The design parameters of human biology were set by evolution on Earth's surface. They are extraordinarily specific to that environment, to one gravity, to a specific range of atmospheric composition and pressure, to a specific range of temperature, to a specific daily cycle of light and dark that has governed circadian rhythms for hundreds of millions of years of animal evolution. Every parameter of the space environment differs from these specifications. Every difference creates a biological cost, and the biological cost scales with exposure time. This is the underlying reason why the dangers of space get worse the further you go. Not only because the physical environment becomes more extreme with distance, but because the time required to traverse greater distances means greater biological exposure to conditions that are not merely uncomfortable, but actively degrading. A 2-week mission to the Moon produces measurable physiological changes, but not disabling ones. A 6-month mission to the ISS produces significant physiological changes, requiring months of rehabilitation. A 2-year Mars mission would produce physiological changes whose long-term consequences at that duration have never been measured, because no human has spent 2 years in space. The combination of duration and environment is what matters. Low Earth orbit for 2 years would produce significant physiological degradation, but not as severe as Mars transit conditions for 7 months, because the radiation environment and gravity conditions differ. The outer solar system for months would be worse than Mars transit. Interstellar space for decades would be worse than anything that has a historical analogue or a meaningful experimental dataset. We are extrapolating from relatively short mission durations. The longest single human spaceflight is approximately 437 days, achieved by Valery Polyakov on the Mir space station in 1994 and 1995, into territory where we have no data. The extrapolation may be approximately correct, or it may miss non-linear effects that only manifest at longer durations. We do not know because the data does not exist. This epistemic gap between what we know from measured data and what we are extrapolating into unmeasured territory is itself one of the most significant dangers of long-duration spaceflight. Planning a mission based on extrapolations that turn out to be wrong at the timescales involved could be fatal in ways that no amount of in-flight adaptation could correct. Consider a specific scenario. A crew departs for Mars. The transit is 7 months. Based on ISS data from 6-month missions, the physiological effects are expected to be manageable with current countermeasures: exercise, pharmaceuticals, careful monitoring. The crew arrives at Mars after 7 months, with physiological changes similar to those observed after 6-month ISS missions, plus some additional effects from the higher radiation environment and slightly different gravity situation during transit. This scenario is within the range of what current data can support as reasonable. The extrapolation from 6 months to 7 months is small, the conditions are somewhat characterized, the countermeasures are developed. Now extend to a Mars architecture that requires an 18-month surface stay before the return window opens, a common scenario in Mars mission planning because the planetary alignment that enables the return transit only occurs at specific times. 18 months on the Martian surface adds to the 7 months of transit physiological changes. At 18 months on the surface, the crew has now been away from Earth's gravitational environment for 25 months, 2.5 years. At Martian surface gravity, 38% of Earth's, the musculoskeletal loading is intermediate between microgravity and Earth normal. Bone and muscle loss would be expected to be slower than in microgravity, but not zero. Cardiovascular adaptation would continue. The cumulative radiation dose would be accumulating. Then another 7 months of transit home. Total mission duration, 39 months. Over 3 years away from Earth's conditions. No human has been in space for anywhere near this long. No data exists to characterize what the human body looks like after 39 months of combined Martian gravity and transit microgravity and accumulated radiation. The crew that lands on Earth after this mission would be in completely uncharted physiological territory. They would need to readapt to Earth's gravity, which after 39 months away might be a longer and more difficult process than the months-long rehabilitation that current long-duration ISS crews require. Whether they could readapt at all after that duration, whether the cardiovascular system could sufficiently recover its ability to pump blood against full Earth gravity, is an open question that current data cannot definitively answer. This is Mars, the most accessible planetary destination within the solar system, within a regime of distances and travel times that are small compared to anything beyond Mars. Now consider that the entire physiological challenge of a Mars mission, the duration, the radiation, the gravity conditions, the isolation, represents the entry-level version of what deep space travel requires. Everything beyond Mars is longer, more extreme, more isolated, with higher radiation, more complex gravitational conditions, and longer durations. The human body is not a fixed specification. It adapts. That is one of the most remarkable properties of biological systems. But adaptation has timescales and limits. Short-term adaptation, adjusting fluid distribution in microgravity, recalibrating balance in the absence of gravitational cues, adapting to the daily light and temperature cycles of a spacecraft, occurs over days to weeks and is well documented. Long-term adaptation, structural changes to bone, cardiovascular remodeling, changes in immune function, occurs over months and is increasingly well documented from ISS missions. Very long-term adaptation, what happens to the human body over years to decades in space, is essentially undocumented because the data does not exist. Whether the human body can adapt to extended spaceflight in ways that make it viable over decade-long mission durations, or whether the degradation continues to accumulate until it becomes disabling, is not known. This is not a gap that can be filled with more careful analysis of existing data. It requires new data, which requires putting humans in those conditions, which is either a mission or a controlled experiment with ethical implications that no institution has been willing to accept. Genetic modification and biological enhancement have been proposed as potential solutions to the human body's mismatch with the space environment. If the bones could be modified to maintain density without mechanical loading, if the cardiovascular system could be recalibrated for microgravity function, if the radiation sensitivity of DNA could be reduced, the biological costs of spaceflight would decrease. This research is in early stages. Some modifications that reduce radiation sensitivity in animal models have been identified. Some approaches to preventing bone loss through pharmaceutical and biological interventions beyond current countermeasures are in development. Whether such modifications are ethically acceptable, practically achievable for human spaceflight applications, and actually effective at the scales needed for multi-decade missions is a cascade of open questions whose answers are not near-term. And even if they were answerable and the answers were positive, implementing them would require regulatory frameworks, safety evaluation timescales, and societal acceptance processes that add decades to any implementation timeline. The alternative, not modifying the biology, but instead eliminating the need for continuous human presence through artificial hibernation, has been explored in both research and popular discussion. Suspended animation, reducing metabolic processes to a level at which decades of spaceflight consume negligible resources and produce negligible physiological effects, would in principle solve both the biological degradation problem and the resource consumption problem simultaneously. If the crew could be maintained in a state of minimal metabolic activity for the transit and awakened at the destination, the physiological cost of the transit would be minimized. The food and water requirements would be dramatically reduced, and the crew would arrive at the destination in approximately the condition they left. Whether this is achievable for humans is currently unknown. Natural torpor in hibernating mammals, bears, ground squirrels, demonstrates that significant metabolic reduction is biologically possible. Extended torpor for periods of weeks to months occurs naturally, but extending this to years or decades is qualitatively different from what any natural biological system achieves. The technical challenges of maintaining human biology in a stable, low metabolic state for years, preventing ice crystal formation in tissues if deep cooling is used, maintaining sufficient metabolic activity to prevent cellular degradation while reducing it enough to be practically useful, ensuring reliable awakening with full neurological function after years of torpor, have not been solved. NASA has funded some research into induced hypothermia for long-duration spaceflight, specifically targeting a state of mild hypothermia at approximately 32 to 34 degrees Celsius for periods of weeks, sufficient to reduce metabolic rate and resource consumption for interplanetary transits within the solar system. This is less than full suspended animation, but provides some of the benefits. Whether it can be extended to months or years, and whether the physiological effects of the hypothermic state itself over those durations are acceptable, is not established. The picture that emerges from all of this, from the physics of radiation and propulsion, from the biology of physiological degradation, from the engineering of life support systems, from the psychology of isolation, from the sociology of small group dynamics, from the economics of civilizational commitment, is consistent. Space does not become more hospitable as you venture further into it. It becomes less hospitable in ways that are not linear. The rate of increasing danger accelerates. The biological costs compound. The engineering requirements multiply. The institutional challenges grow. This is not a reason to stop going. It is a reason to understand clearly what going means at each scale, what is being attempted, what the actual requirements are, what the realistic costs in engineering and biology and time and resources are at each step. The romanticized version of space exploration, the version in which better rockets and brave crews venture outward into an inspiring but fundamentally similar environment, discovering new worlds and expanding human civilization, misrepresents the actual physical situation in ways that matter. Not because the destinations are not real or because exploration is not valuable, but because the nature of what is required to reach those destinations and survive within them is qualitatively different from what the romantic version implies. The gap between the romantic version and the physical version is itself one of the most important things to understand about space. Not because the physical version is discouraging, it is, if anything, more interesting than the romantic version, because the challenges are more fundamental and the eventual achievement of overcoming them more significant. But because accurate understanding of the actual challenges is a prerequisite for making realistic decisions about how to approach them, a civilization that believes interstellar travel is simply a matter of building a bigger rocket will make different choices about what to invest in than a civilization that understands the actual landscape of challenges, the radiation biology, the life support engineering, the psychological constraints, the propulsion physics, the communication delays, the civilizational commitment required. The first civilization will be perpetually surprised by how hard it is. The second will be working on the right problems. The right problems are not small. They include fundamental questions in nuclear physics, how to achieve controlled fusion at the energy densities required for meaningful propulsion. They include fundamental questions in radiation biology, what the long-term effects of galactic cosmic ray exposure are on human neurological function, and whether biological or technological countermeasures can reduce them to acceptable levels. They include fundamental questions in closed-loop ecological engineering, whether a self-sustaining life support ecosystem can be built and maintained at the scales required for multi-year or multi-decade missions. They include fundamental questions in materials science. What materials can provide adequate radiation shielding at practical mass and volume while surviving decades in the space environment? They include fundamental questions in medicine. Whether the physiological degradation of extended spaceflight can be arrested at levels that preserve functional capability over mission durations measured in years. None of these questions are unanswerable. Each of them is being worked on to varying degrees by research programs around the world, but none of them are close to resolved, and resolving them would require sustained investment over timescales measured in decades, not years. The universe has a particular relationship to haste. It does not care about timelines. It does not become more accessible because someone wants to get there faster. The distances are what they are. The radiation is what it is. The laws of physics are fixed. The human relationship to those fixed constraints is the variable. The rate at which understanding improves, the rate at which engineering capability advances, the rate at which biological challenges are characterized and potentially mitigated, these are not fixed. They respond to investment, to prioritization, to the accumulation of knowledge that each mission and each experiment and each theoretical advance contributes. The Apollo program, in 12 years of intensive effort from first crewed flight to lunar landing, achieved something that had seemed impossible from the outside. Not by changing physics. The physics was fixed before Apollo started and remained the same throughout. By acquiring understanding, developing engineering solutions, and accepting a level of risk that reflected the judgment that the goal was worth the cost. The judgment that any given goal in space exploration is worth its cost is not a scientific judgment. It is a human judgment about values, about priorities, about what is worth attempting given what the attempt requires. The scientific and engineering analysis can characterize what the attempt requires as accurately as current knowledge allows. The judgment about whether that requirement is worth meeting is made by people, not by physics. What the physics says clearly is that the further you go, the more it requires. At every step, something that worked at the previous scale stops working, and something new must be developed to replace it. At every step, the margin for error decreases because the consequences of failure scale with the distance from any possibility of rescue. At every step, the universe is exactly as indifferent as it was at the step before. It provides no encouragement and no discouragement. It simply continues to be what it is: vast, hostile to biology at all but the most locally specific conditions, governed by laws that are the same everywhere and that favour neither exploration nor its abandonment. The encouragement, if any exists, is entirely internal to the species attempting the exploration. It comes from the same source that drives any attempt to understand and navigate environments that were not designed for human habitation, from whatever combination of curiosity, ambition, and occasionally poor risk assessment has been characteristic of the species since long before it had any concept of what space was. That combination has produced, in the roughly 65 years since the first human reached orbit, a species that has visited the Moon, sent robotic probes to every planet in the solar system, placed a spacecraft in interstellar space, detected gravitational waves from black hole mergers a billion light-years away, imaged the supermassive black hole at the centre of the Milky Way, and characterized the atmospheres of planets orbiting stars dozens of light-years away. None of this required overcoming the indifference of the universe. The universe remained indifferent throughout. It required overcoming the limits of what the species could understand and build and operate, limits that turned out to be more flexible than they appeared at each stage, though always less flexible than optimism suggested they would be. The limits that currently define the boundary of what is accessible, Mars with significant physiological risk, the outer solar system robotically but not with human crews, the heliopause just barely with 50-year-old technology producing the first data from interstellar space. These limits are not permanent. They are the current state. Current meaning at this specific moment in the development of the species and its technology. Whether and how quickly they change depends on choices that are being made now and will continue to be made by institutions and individuals who are collectively determining where resources go and what problems are prioritized. The physics of what would be required to extend those limits is well enough understood to identify what needs to be developed. The biology of what the human body can tolerate at extended durations in deep space is not well enough understood and requires data from missions that have not yet been conducted. The engineering of what life support systems can achieve at the scales required for very long-duration missions is not well enough characterized and requires development programs that are not currently funded at the levels required. The propulsion physics required for meaningful interstellar velocity requires either controlled fusion, still not achieved after 7 decades of effort, or something more exotic that is not currently on the near-term technological horizon. These are not small gaps. They are not problems that will be solved next year or in the next decade. They are the actual shape of what stands between where we are and where we would need to be to extend human presence meaningfully beyond the inner solar system. And they are precisely the shape of the problem that makes it interesting. The universe does not get less interesting as you understand it more clearly. The challenges do not become more discouraging when you understand them accurately rather than romantically. The accurate understanding is, in fact, more remarkable, because the scale of what is required to survive at increasing distances from Earth's surface reveals how specifically and improbably calibrated Earth's environment is for biological life, and how far outside that calibration the rest of the universe lies. We are a thin membrane of biological complexity floating on the surface of one small rock, surrounded on all sides by an environment that becomes more lethal at every step away from that surface. The membrane has, in the last few decades, learned to look outward and measure what is there. It has sent small, robotic extensions of itself to the edges of the solar system and into the space beyond. It has begun to understand what would be required to extend the membrane itself, not just its robotic proxies, into that environment. What would be required is enormous. What has already been achieved is also enormous. The gap between the two is honest and large, and defines the frontier as it actually exists, not as romanticized imagination would have it, but as physics and biology and engineering and human psychology have made it. The further you go, the worse it gets. And the understanding of exactly how much worse and in exactly what ways is the beginning of knowing what would have to be true to change it. Let us talk about what happens to time itself as a danger. Not time dilation in the relativistic sense, which we have already touched on, but time as an operational constraint that becomes progressively more severe with distance, in ways that have nothing to do with relativity and everything to do with the practical reality of operating complex systems far from any support infrastructure. On Earth, when a complex system fails, a power grid, a medical device, a structural component in a building, the response time for expert intervention is measured in hours at most. In most cases, minutes. The entire accumulated expertise of human civilization is available to address any specific failure mode through a global network of specialists, spare parts, manufacturing capability, and transportation infrastructure. If a specific component fails in a specific way that has never been seen before, engineers who have spent their careers on that system can be assembled in hours to diagnose and respond. This response capability, the ability to bring expert attention and physical resources to bear on a specific problem within hours, is so embedded in how modern technological systems are designed that its absence is not typically considered as a design constraint. We design systems with the assumption that expert support is available when things go wrong in unexpected ways. Remove that assumption, and every system you rely on must be completely self-contained in its repair capability. At the International Space Station, the most technologically complex crewed spacecraft in history, failures occur regularly. Not catastrophic failures, but the steady accumulation of component degradation and unexpected behavior that characterizes any complex engineered system operating continuously. In just the last several years, the ISS has experienced a leak in the cooling system of a visiting Russian spacecraft. A crack that appeared in a module's hull and was located and patched. Malfunctions in the toilet water recovery system. Issues with the oxygen generation system, and numerous smaller equipment failures. In each case, the response involved a combination of crew actions guided by ground controllers who could provide real-time diagnostic support and, when necessary, replacement components delivered on subsequent resupply missions. The crew is capable of performing many repairs autonomously. They train extensively for this. But the institutional support of thousands of engineers and technicians on the ground who can analyze telemetry, consult historical failure data, develop repair procedures, and provide step-by-step guidance is what makes the ISS's survival rate for component failures so high. Strip away that ground support, and the response to any unexpected failure must come entirely from the knowledge and materials present on the spacecraft. This is manageable when the failure modes are well characterized and spare parts are available, both conditions that careful mission planning can partially achieve. It becomes progressively less manageable as the mission encounters unexpected failure modes that no one anticipated, which is what complex systems routinely do over long operation periods. The mathematical reality is that a system with many components, each with a small probability of failure per unit time, has an overall probability of experiencing at least one component failure that approaches 1 over sufficiently long timescales. The ISS has thousands of components with failure probabilities that are individually small, but collectively sufficient to ensure multiple component failures per year. Managing this failure rate with current ground support is already a significant operational challenge. Managing it with no ground support, no resupply of replacement components, and a crew whose skills are necessarily generalist rather than specialist in every subsystem is categorically more difficult. The canonical planning approach for this challenge is graceful degradation, designing systems so that any single component failure reduces capability without ending the mission, and any pair of component failures reduces it further without making it immediately fatal. And only after a sequence of failures that individually might each have probability of 1 in 100 does the mission reach a configuration from which it cannot recover. This is good engineering philosophy, but implementing it for a spacecraft that must survive for decades in an environment that will stress every component continuously while being maintained by a crew that cannot be supplemented or replaced is a design challenge that current engineering has not solved. There is also the problem of knowledge decay. A crew member trained as a spacecraft systems engineer before departure will be the same person who must diagnose a novel failure mode 15 years into an interstellar transit. Their knowledge will be 15 years old. The context that makes their training meaningful, familiarity with the original design documentation, the ability to consult colleagues who worked on the original system, access to engineering databases and analysis tools, will be degraded or absent. They will have the knowledge that was in their head at departure, plus whatever they have learned during the transit, applied to a system that is now 15 years older and may have failed in ways that no pre-departure training anticipated. This is not a problem unique to space travel. Any long-duration, isolated operation faces similar knowledge management challenges, but the severity scales with the isolation and the duration. Antarctic crews can be replaced annually. Submarines return to port within months. Neither faces the situation where the knowledge required to maintain a critical system 15 years from now must be carried entirely by crew members who are 15 years removed from their last contact with the engineering community that designed the system. Institutional knowledge, the accumulated understanding of how a specific system behaves under specific conditions, built up over years of operation and documented in engineering records and carried in the experience of the people who work on it, is one of the most valuable and fragile assets in complex system management. For an interstellar mission, this knowledge must be completely portable and completely self-refreshing, carried by the crew members who cannot be supplemented and preserved in documentation systems that must themselves remain functional for the entire mission duration. The problem of institutional knowledge in long-duration, isolated missions has a terrestrial analogue in the nuclear power industry, where the safe operation of reactors depends partly on accumulated operational experience that is difficult to fully document and that can be lost when experienced operators retire faster than new operators can absorb the tacit knowledge that makes experience valuable. The nuclear industry manages this through extensive training programs, detailed documentation, regulatory oversight, and, critically, the ability to consult experienced operators who may be retired but remain reachable. None of these management mechanisms are available to an interstellar crew. Now let us talk about something that is rarely discussed in the context of space travel, but that represents one of the most fundamental dangers at truly large distances: the danger of irreversibility. Every step further from Earth increases the cost and difficulty of returning. At low Earth orbit, emergency return takes hours and is a designed-in capability of every crewed mission. The Soyuz capsules docked to the ISS are continuously ready for emergency evacuation. At the Moon, return takes 3 days and requires a functional lunar module or equivalent. The Apollo 13 mission demonstrated that a crew could survive a catastrophic system failure and return from the Moon. Barely, because the return capability was physically present, even if damaged. At Mars, return requires waiting for a planetary alignment that only occurs every approximately 26 months, operating a return vehicle that has been waiting on or orbiting Mars for the entire surface stay, and surviving a 7-month return transit. A sequence of dependencies such that failure of any one of them strands the crew permanently. Permanent stranding at Mars is a scenario that has been seriously discussed in the context of Mars mission planning. Some mission architectures, particularly those proposed by private entities, have explicitly or implicitly accepted that a first crew might not return, either because the return capability is not included in the mission design, or because the failure probability over the full mission is high enough that planning for non-return is more practical than planning for successful return. This is a qualitative departure from every previous human spaceflight paradigm, in which the ability to bring the crew home was a non-negotiable requirement of mission design. Beyond Mars, the concept of return becomes progressively more complex until it approaches impractical for any near-term mission architecture. A crewed mission to Jupiter would require transit times that make the round-trip duration extraordinary, propulsion systems that do not yet exist for the required velocities, and life support systems that would need to function for years without the intervention that current life support systems require. A crewed mission to the outer solar system is not currently in any realistic planning horizon, not because it is permanently impossible, but because the gap between current capability and required capability is too large to bridge with foreseeable near-term technology. The universe did not arrange itself for our convenience. This is not a philosophical observation, it is a physical fact with measurable consequences. The radiation environment at Mars delivers doses that exceed current career limits for astronauts in a single mission. The radiation environment at Jupiter would kill an unshielded human in hours. The communication delay to Neptune exceeds 8 hours each way. The energy required to reach the nearest star at any velocity that makes the journey human feasible exceeds current global annual energy production by orders of magnitude. The biological systems that make a human being were calibrated over 4 billion years to function at one specific gravity, under one specific atmospheric composition, within one specific temperature range, on the surface of one specific planet. None of this changes based on how much we want it to be otherwise. And yet, the same species that evolved to walk on grass and sleep in caves and navigate by stars they could not explain has, in the last 65 years, placed 12 of its members on the surface of another world and brought them home. It has sent robotic extensions of itself to every planet in the solar system. It has crossed the heliopause with a machine built with 1970s technology that is still transmitting data from interstellar space. It has imaged the atmospheres of planets orbiting stars 40 light-years away. it has detected the gravitational ripple of two black holes merging 1 billion years ago and 1 billion light-years distant. It did none of this by ignoring the physics. It did all of it by understanding the physics well enough to work within it. The progression of danger outward from Earth is real. Low Earth orbit is manageable. The Moon is harder. Mars is at the edge of what current technology can support with acceptable risk. The outer solar system is beyond what current technology can support for human presence. Interstellar space is beyond what any near-term technology can support for anything except the most minimal robotic probe. These are not opinions. They are the current state of a specific relationship between human capability and physical reality. The physical reality is fixed. The human capability is not. Every barrier that has been crossed in the history of space exploration required developing capabilities that did not exist before the barrier was crossed. The capability to reach orbit did not exist before it was developed. The capability to sustain humans in space for months did not exist before it was developed. The capability to navigate to and land on another world did not exist before it was developed. Each capability required understanding what was specifically needed, investing in developing it, accepting the failures that occur during development, and ultimately arriving at something that worked well enough to cross the barrier. The barriers ahead are larger. The capabilities required are more fundamental in nuclear physics, in radiation biology, in closed-loop life support engineering, in propulsion, in human physiology, in the social organization of isolated communities under extreme stress. The timescales are decades to centuries rather than years to decades. The investment required is larger than what has been made for any previous space program. None of that makes the barriers permanent. It makes them the current frontier. There is something clarifying about understanding the dangers of deep space honestly. Not the romantic version, where the frontier is vast and inspiring, and human ingenuity will find a way, and not the pessimistic version, where the barriers are so extreme that the attempt is pointless. The honest version, in which the barriers are real and large and specifically characterized, and the capability to cross them is not yet in hand, but is not physically forbidden. And the investment required to develop that capability is known, if not yet committed. The honest version is harder to find inspiring than the romantic version. It does not come with the emotional resonance of heroic exploration narratives. It comes instead with a different kind of significance, the significance of understanding what is actually there, what it would actually take, what the genuine cost of going further actually is. That understanding is the prerequisite for doing anything real about it. You live at the bottom of the stack, on the surface of the one planet in the known universe specifically calibrated for your biology. 400 kilometers above you, less than the distance from one major city to another, the environment becomes immediately lethal without life support systems. 38 million kilometers away, at Mars, it becomes marginally survivable with current technology. 778 million kilometers away, at Jupiter, it becomes lethal even with substantial shielding. 40 trillion kilometers away, at the nearest star, it is effectively inaccessible with any near-term technology. This is where you are. This is what surrounds you. This is the actual scale of the accessible universe versus the observable universe, the stunning, profound, permanently relevant gap between everything that can be seen and nearly nothing that can be reached. And within that gap, in the space between what is known and what is reachable, between what is observed and what is accessible, is the entire project of expanding human presence in space. Not as it is romanticized, but as it actually is. Large, difficult, expensive, requiring sustained investment over timescales that exceed individual careers and institutional planning horizons, making demands on human biology and social organization that evolution did not prepare us for, governed by physical laws that do not yield to enthusiasm or optimism or even brilliance applied at insufficient scale. The further you go, the worse it gets. Understanding exactly how much worse, and in exactly what ways, and what would need to be true to change it, is where the actual work is. Not the inspiring speeches, not the renders of spacecraft that do not yet exist. The physics, the biology, the engineering, the investment, the decades of sustained effort at sufficient scale to move the capability from where it is to where it would need to be. The universe is waiting. It has been waiting for 4.5 billion years since this planet formed. It will wait for billions more. It has no preference about whether we cross the barriers it presents. It does not care. We are the part of the universe that cares. The only part we know of. The only pocket of self-awareness embedded in 400 cubic kilometers of breathable atmosphere on one rocky planet, surrounded on all sides and above by environments that become more hostile at every meter of altitude, capable of observing everything and reaching almost nothing. That gap between observation and reach, between what is known and what is accessible, is not a permanent feature of the human situation. It is the current feature. Current meaning now, at this specific moment in the development of a species that has been technologically capable of leaving its planet for 65 years. 65 years is not long. Not against the 4.5 billion years of this planet's history, not against the 13.5 billion years of the universe, not against the billions of years remaining before the sun exhausts its fuel. There is time. There is also, as there has always been, the question of what the time is used for. The further you go, the worse it gets, and the worse it gets, the more precisely it can be understood. And the more precisely it can be understood, the more directly it can be addressed. That is the only trajectory that has ever worked.